Hello and welcome to today's lecture. This is lecture number 47 of our course on blockchain and its applications. And today we are going to continue our discussions on blockchain interoperability, which we started in our last lecture. So, this is the second lecture on this topic of blockchain interoperability. So, today we are going to cover these concepts. First of all, we will talk about cross-chain asset exchange, what it means, how we can do it, and in that context, we will talk about what is meant by atomic swap. If you remember, we initiated our discussion on atomicity of these operations, and as I said, it is similar in concept to the property of atomicity of transactions in the context of databases. We will see how we can use these concepts like hash lock and time lock and also hashed time lock for ensuring such atomic swap, and in the process we will have detailed protocol description of atomic exchange. The keywords for today's discussion are atomic exchange, of course hash lock and time lock, and as I mentioned, a combination of these hash lock and time lock in forming what is called hashed time lock contract or HTLC, and then we will introduce our discussion on atomic exchange, and in this lecture we will talk about only two parties where there will be some exchange of such cryptocurrency and this is only between two parties and in different blockchain networks, and in our next lecture we will talk about how to carry out atomic exchange for more than two parties. So, let us try to understand what is meant by this cross chain asset transfer using atomic exchange. So, if we look at this particular diagram, we see that there are two networks. On one side we have the Bitcoin network. So, this is the Bitcoin network, and on the other side we have the Ethereum network, and then in the Bitcoin network, Alice the sender sends one Bitcoin as an example, it could be any number of Bitcoins of course, to Jack, which is acting as the exchanger. And on the Ethereum network, on the other side, this Jack will be sending an equivalent amount, which is for example 33 ethers from his account to Alice. So, if you look at this, that Alice on this side is the sender as is written here, okay, and then finally it will be transferred to Bob. So, these 33 ethers indeed would be going to Bob, but for that what we are doing is that Alice is using an exchanger Jack, and this amount of one Bitcoin is first going to Jack in this Bitcoin network, and at the same time it is going from Jack to Alice the equivalent amount of 33 ethers. And finally, of course, Alice will be transferring those 33 ethers to Bob, which is the final intended recipient of this transfer of asset. So, we see that this is indeed an example of cross chain asset transfer. What is very important is that in order that it works correctly and no party can back out in between, or there is no issue about the exchange rate between Bitcoin and Ethereum, this ether fluctuation, these two cryptocurrencies, their exchange rates fluctuate and having an impact on the final transfer. What we need to ensure is this part, that 1 and 2, that should be atomic exchange. That means the operation of Alice transferring one Bitcoin to Jack in the Bitcoin network and Jack transferring 33 ethers to Alice in the Ethereum network, they should be carried out atomically, and once it is there with Alice, so it means what Alice in effect has transferred equivalent of one Bitcoin, which is this 33 ethers from her account in Bitcoin network to her account in the Ethereum network, and once these 33 ethers are there in Alice's account in the Ethereum network, Alice can later on transfer in this step 3 these 33 ethers to Bob. So, what is important is that this 1 and 2 should be atomic exchange, and after that the transfer can take place, but even after these two steps 1 and 2 are carried out, in case that step number 3 is delayed, it is not a problem, because in fact from the beginning Alice has been able to get those 1 Bitcoin transferred to our account, that is the equivalent of 33 ethers in the Ethereum network. So, if we can solve the atomic exchange problem, it will solve the most of the challenges in asset transfer across multiple such blockchain networks. So, we will see how actually this can indeed be carried out. So, we will discuss about one particular work, research work that was carried out and it was published in this PODC 2018 conference, which is one of the seminal work in this area, and we will refer to this particular paper. We will have details of that in our subsequent slides. So, what it does is that it talks about atomicity. So, atomic transaction, as we have defined, is an indivisible series of operations such that either all of them occur or none occurs. And atomic swap protocol that we will discuss, it guarantees that if all parties conform to the protocol, then all swaps take place. If some of the parties deviate from the protocol, then no conforming party ends up worse off. And finally, no coalition has an incentive to deviate from the protocol. So, what do they mean? It means that as long as we have this protocol in place and all the parties who are participating in this protocol in that atomic cross chain swap, so if all of them are conforming to the protocol, then the swaps will take place. It is guaranteed. However, if in the process, if some of the parties deviate from the protocol, then the parties who are not deviating, the ones who are conforming to the protocol, they should not have any difficulty. So, they should not be worse off, meaning that with respect to what they had before the protocol execution was started, so they should not end up being worse off at the end of the execution of the protocol. And of course, that it means that, so no conforming party would end up being worse off. So, it may so happen that the actual exchange does not take place, but that is fine as long as there is no situation in which those who are conforming, they got their payments deducted, but they did not get back in anything in return. So, that should not happen. And no coalition, like if some of the people try to form a coalition, then by doing that also they should not be able to gain much. So, there should not be any incentive to form a coalition that would try to deviate from the set protocol. So, we will see how it actually works. So, let us take a look at this basic idea. What we have here is that we have, of course, in terms of smart contracts. So, we have these smart contracts, multiple smart contracts that will be written. So, let us see how the smart contracts would actually work conceptually. Of course, one has to write the smart contract codes in the appropriate language of these networks. So, what is done is that these smart contracts are initialized on both ends with the amount. So, if you see this diagram here, so Alice initiates this smart contract, which is denoted as contract A in the Bitcoin network, which is about transferring those 1 Bitcoin. And then Bob in the Ethereum network initiates this contract B that transfers 33 ethers. So, in this example, what we are doing is that here we are taking a situation where Alice would be transferring 1 Bitcoin to Bob and Bob would be transferring 33 ethers to Alice. Okay. And let us assume for the time being, it is in this situation, this Bob is like that exchanger that we talked about in the previous slides. So, this is going to happen. Both, remember, both Alice and Bob have accounts in the Bitcoin network and they both also have accounts in the Ethereum network. Okay. So, in the Bitcoin network, so Alice is creating this contract of transferring 1 Bitcoin to Bob. In the Ethereum network, Bob is creating this smart contract to transfer 33 ethers to Alice. So, up to this we have the first 2 steps. Now, after these contracts have been created, then on occurrence of a common event trigger, what will happen is that contract A will get executed transferring 1 Bitcoin to Bob, and also at the same time atomically contract B also will get executed, transferring those 33 ethers to Alice. So, what is most important in this whole diagram is that this common event trigger would cause both the contracts to be executed simultaneously, and they will be executed as a result in atomic fashion, as we will see how indeed this can be guaranteed. So, let us first see that if we consider this type of an operation, how we can make use of these hash lock and time locks to ensure such atomic transfer of assets. So, we introduce the concepts of hash lock and time lock. Hash lock, it is a function that restricts the spending of funds until a certain piece of data is publicly disclosed, which acts as a cryptographic proof. So, how it works is like this, that say there is a pre-image X. So, let us recap our discussions on cryptographic hash functions. So, if there is, we said, a message M which has got a hash HM. So, similarly, we are talking about the pre-image, say X, which has got a hash of HX. Okay. So, this secret pre-image will denote it, say, by X. So, this hash of X, which is HX, which we could denote as Y or H or something, which is essentially hash of X. So, that is posted as a hash lock. So, what is done is that it is like locking some spending of a cryptocurrency based on this hash that we are going to use. And initial locking, remember, it is very simple. The locking is done using the hashed value, and unlocking can be done using the pre-image. So, if X and HX are the pre-image and the hash of X respectively, then locking can be done using HX and unlocking can be done using X. So, till the time X is made available, this cannot be unlocked. That means, the payment cannot be released in the transaction, but the smart contract can be deployed, which would say that when this X is revealed, then the payment would be released, but till that time an amount of whatever say of 1 Bitcoin or 10 Bitcoin or whatever, or 33 ethers. So, this payment can be guaranteed by ensuring that it is locked using HX, and it can be unlocked only by revealing this pre-image, which is X. And time lock is that if, for example, this unlocking is not done, then after a certain period of time, then that fund can be returned back to the original issuer. So, also it can be used in such a way that unless that time actually reaches, then the spending of fund will not be allowed. So, as we will see that this concept of hash lock and the concept of time lock can be nicely combined in this concept of hash time lock. So, independently, if we look at time lock, it can restrict spending of funds until a specific time, which could be also equivalent to block height. So, this time need not always be a clock time, it could be in terms of block height. If you remember what is meant by block height, that is that number of blocks that have been added in a particular blockchain network, like we discussed about this number of block number in the Bitcoin network in detail. Also remember that this is not something new that you are learning. When we discussed about transactions in the context of Bitcoin, there we talked about this script pub key and script sig, where we indeed took this example of a particular script. If you remember, we talked about some interesting scripts, and there was one such script that said that unless that time is reached, the script sig will not be able to unlock that amount. That means, the recipient will not be able to claim that amount. What it means is that I can put this particular condition that this fund can be used only after the specified time has been reached, and hash lock is one that would ensure that till the pre-image is revealed, this money cannot be used, or this particular currency cannot be used or claimed by the recipient. So, what we do here is that we now see that how they actually work. So, as we said that hash lock is a type of encumbrance. So, it is there which is blocking something that restricts the spending of an amount until a specified secret key is publicly revealed. What is very important, and that is the foundation for this cross-chain atomic swaps, is that this inherent property that once any hash lock is opened publicly, that means the pre-image of that hash is revealed, any other transactions which were done which also use the same hash lock, that means same value of the hash of the pre-image, all of them will now be opened. So, let x be the pre-image, hx be its hash, and using hx, say contract A is locked, also contract B is locked, and when x will be revealed, then contract A will get executed and at the same time contract B also will get executed. That means, if contract A transfers 1 Bitcoin from Alice to Bob and contract B transfers 33 ethers from Bob to Alice, as soon as this x is revealed, both of these contracts will execute and Bob will get 1 Bitcoin in the Bitcoin network, and as it is also presented in the Ethereum network, then Alice would get 33 ethers in the Ethereum network. So, that is the inherent property of hash locks. So, we give an example. Alice generates a secret key, say it is this x that I was talking about, I love strawberries, and then Alice computes the cryptographic hash of this key and say this is this encoded form of the hash, and now Alice initiates a hash locked contract of 1 Bitcoin, and which has the condition that if key is revealed, 1 Bitcoin would be paid to Bob. And the contract also contains the hash which allows any miner to verify the revealed key, so that it should not happen later on Alice will say something else to be the secret and then say that no, this cannot be claimed. So, it is important that when it is revealed, any miner can verify that hash of this key that is now revealed indeed maps to what was the hash that was used in the contract. So, as always that in the context of blockchain operations, we would always be in a position to verify whatever has been initially claimed to be the hash was indeed the hash once we get the key revealed. So, if the hash of that revealed key does not match with this hash that was there with the contract, then we know that something is not correct. So, that means that this is not the actual key that was used to create that particular contract in the first place. So, that is how we will see it works. So, let us see that in time lock, in contrast, it is a smart contract primitive, as we said, which restricts the spending or transfer of some currency until a specified future time. And as mentioned, that block height can be used as a proxy for time. So, if we take an illustrative example, so Alice can generate a time locked contract with 1 Bitcoin with say time equal to 2 delta, where delta is some time unit. What will happen is that after 2 delta time, this 1 Bitcoin will be transferred to a target account. So, the contract would be written in such a way that it could be, say Alice would say that this contract I have written, and then at the end of say 2 delta time. So, 2 delta I say it is 2 hours. So, let us assume delta is 1 hour. So, that means that the contract would be such that say it is published at 5 p.m. on 25th of October 2021, and it says that after 2 hours then the payment would be made. So, that means that at 7 p.m. on 25th October 2021, the payment can be made from Alice's account to Bob's account, and that of course will be done automatically by the smart contract. Also, what can be done is that this target account need not be a different account, it could indeed be Alice's own account. So, what can be done is that after 2 hours we can say that the money will revert back to Alice's account itself. Now, finally, we combine this hash lock and time lock into what is called hash time lock contract. What we see here is that we have this contract created by Alice, the funding contract, which is of 1 Bitcoin. It has got a hash which is something like this as is written, and then there is a timeout of 2 delta. So, what happens is that it says that after the key is revealed, or if the key is revealed, then this 1 Bitcoin will be transferred to Bob. Also, it says that there is a timeout of 2 delta. So, that is the time lock is for a period of 2 delta, and then let us assume again it is 2 hour. So, that means that if Alice reveals the key, and which in this example that we took is the key is I love strawberries, then after Alice reveals the key, so till the time Alice reveals the key, Bob cannot claim that amount, and say after 1 hour of creating the contract, Alice reveals the key to Bob, and why 1 hour? Maybe Bob would provide some service to Alice and then only Alice would release this key. And why would that happen? It could be that Bob is maybe selling something to Alice or providing some service to Alice, and then once that service is given, then Alice would reveal the key, and once Alice reveals the key, then Bob would be able to claim that 1 Bitcoin, and that is how the entire operation will take place. The transaction would take place that Bob provides some service to Alice or sells something to Alice, and Alice makes the payment in Bitcoin to Bob. Remember that Bob would provide the service only after Alice has not only created that contract is like a transaction in the blockchain network, and then this particular transaction is there sufficiently deep in the network. That means, after this particular transaction was mined in a block and more such blocks were added after that, that means that now Alice cannot go back and change that contract. So, only when that happens, Bob is very sure that Alice cannot go back on her promises of paying that 1 Bitcoin, and then only Bob would provide that service. Once Alice gets that service, Alice would reveal the key I love strawberries to Bob, and Bob will now be able to enter that along with his signature. Of course, that Alice made the payment to Bob using Bob's public key, maybe hash of the public key. So, Bob provides the signature and the key. So, now this hash locked contract will now be unlocked and Bob gets the amount. But suppose what happens is that Bob does not make the provide the service to Alice. So, Alice created the contract promising to pay 1 Bitcoin if she got the service from Bob, but Bob finally did not provide the service or did not supply the item. So, in that case what would happen is that now you see that Alice's 1 Bitcoin is locked in that contract. So, what needs to be there is that there is this notion of now timeout. When what it says is that after this 2 delta, which is say 2 hours, when Alice of course will not reveal the key because she did not get the service or the item from Bob. So, Alice, instead of revealing the key, Alice would just wait, and after 2 hours, assuming delta is 1 hour, then this contract will time out, and then this 1 Bitcoin will be reverted back to Alice. So, the contract would be written in such a way that after this time, that when the timeout timeout occurs, then the money will be paid back to Alice. So, you see that in either case, by doing this, by combining hash lock and time lock into this hash time lock contract, we are ensuring that Bob will get the money or that cryptocurrency if he provided the service, because then only Alice would reveal the key, and if something goes wrong, after some time Alice will get back her 1 Bitcoin. So, that is the beauty of this hash time lock contract. So, we will see how this hash time lock contract is indeed used for atomic swap. So, we have just given an example where, if you see here, it is only one sided, that Alice is making the payment to Bob, and as I explained that the payment will be made because Bob might be providing service, and we are treating that service is happening off chain. That means, it is not something that we know in the blockchain itself. Now, then what we do is that we see how this hash time lock contract concept can be used for atomic swap. So, where Alice will transfer 1 Bitcoin to Bob and Bob will transfer 33 ethers to Alice, and these two will take place atomically. Again, just to put it in proper perspective, we are assuming that both Alice and Bob have accounts in the Bitcoin network, and they also have account in the Ethereum network. So, in the Bitcoin network, Alice is transferring 1 Bitcoin to Bob, and in the Ethereum network, Bob is transferring 33 ethers to Alice. So, what do we see here is the steps that generate the secret, which is generate the secret key, and then compute the hash, that is what Alice does, and then Alice creates the contract, and which is an HTLC, that means a hash time lock contract with 1 Bitcoin, the hash of the corresponding secret key, and then there is say a timeout of 4 delta. And then what happens is that Alice would say that this is the H, that is the hash of the pre-image that was used to create the contract. So, Bob now can verify that indeed Alice created the funding contract HTLC with that H. So, Bob can verify that, and once Bob verifies that, then Bob is sure that now Alice cannot go back on her promise, because it is now they are deeply buried in more number of blocks after the block in which that contract went in as a transaction. So, what happens is that now once Bob is satisfied with that, what Bob will do is that Bob now creates this contract where Bob now puts this in the Ethereum network. So, you see that this was in the Bitcoin network and now this is in the Ethereum network, and Bob now creates another HTLC contract of 33 Ether, transferring it to Alice, which has very importantly the same H. So, the same hash is used in this contract also, but it has got a timeout which is a little less than what was there for Alice's contract. And take it like this, that this 4 delta is such that when Alice starts, say Alice starts at say 5 p.m. and 4 delta is such that it will time out at say 8 p.m. Okay. So, 4 delta is say or say at 9 p.m. So, 4 delta is 4 hours. So, Alice's contract will time out at 9 p.m. So, say Bob checks everything and creates the contract at say 6 p.m. and then will set delta such that this 6 p.m. plus 2 delta is less than 9 p.m. So, say Bob sets it as 2 hours. So, Bob's contract will time out at 8 p.m. So, Alice created the contract at 5 p.m., Bob at 6 p.m., Bob's contract will time out at 8 p.m. and Alice's contract will time out at 9 p.m. But let us wait on that. So, let there be no need for timeout. So, what happens is that once Bob has created this contract, as you can see that now Alice will check that Bob indeed has created the contract. It is also deeply buried in more number of blocks, and then Alice is sure that Alice can get those 33 ethers from Bob. So, what Alice does is that Alice would reveal the key, and then by revealing the key, now that means that whatever contract Bob had created, that can be used for claiming only when the key is revealed, but Alice knows the key. So, Alice now reveals the key and claims those 33 ethers. But as we said that as soon as this key is revealed, Bob knows about it, and because Bob knows about it, now Bob will go and then will be using it to get back his 1 Bitcoin in the Bitcoin network. So, by revealing the key, Alice got the money from Bob in the Ethereum network, and then because the key is revealed, Bob knows it, Bob uses it in the Bitcoin network to redeem the 1 Bitcoin that was there in the contract created by Alice. So, 1 Bitcoin gets paid to Bob. So, you see that in this manner, as soon as this key is revealed, then both of the parties can get their own cryptocurrencies, like 1 Bitcoin goes to Bob and 33 ethers go to Alice. What is also important, as we will see in the very next slide, is that it is possible that something does not really work as already explained or as described. So, what if Alice does not reveal the key? So, if Alice does not reveal the key, why might not Alice reveal the key? Because it might be a case, just as an example, that Alice expected Bob to pay maybe 35 ethers, but Bob only created a smart contract saying I will pay 33 ethers. So, Bob is not willing to pay 35 ethers to Alice, which she possibly expected. So, Alice, you see that put this HTLC of 1 Bitcoin, and then Bob checked everything, and then Bob gave his HTLC of say 33 ethers, with which Alice is not satisfied. So, what Alice would do? If Alice now reveals the key, then her 1 Bitcoin will go to Bob and she will get only 33 ethers, but she is not satisfied with 33 ethers. So, what she will do is that she will not reveal the key at all, and if she does not reveal the key, what will happen? After some time, timeout will occur. So, first the timeout of Bob will occur. If you remember, we said that Bob created the contract at say 6 p.m. and the timeout would occur at 8 p.m. So, Bob first gets back his 33 ethers, and then after some time, say at 9 p.m., the contract of Alice will time out and Alice gets back her 1 Bitcoin, that is she is refunded her 1 Bitcoin. So, you see that if something goes wrong in between, okay, and even that Alice had added and Bob did not do it, okay, and as a result it is to be ensured that when, as we said, that when the parties do not follow the protocol to its final completion, then also they should not be worse off for some reason that they are not happy and they do not complete the protocol, then you see that both get back their money. You have to notice one point, the example that I gave is that Alice's timeout is at 9 p.m. and Bob's is at 8 p.m. So, it is important that this happens, otherwise what could have happened was, if for example, Alice's timeout was after when Bob created the contract. In our example, Alice created the contract at 5 p.m., Bob at 6, and say Alice's timeout is such that it will time out at 7 p.m. So, what can happen is that Alice can wait till 7 p.m. when her contract times out, she gets back her Bitcoin. Now, by revealing the key, she can also get the 33 ethers that Bob has created in his contract for Alice. But then by that time, because Alice has timed out and has got back her 1 Bitcoin, so what will happen is that Bob cannot now claim those that 1 Bitcoin from the contract, because it has already timed out. So, it is very important that these different timeouts are appropriately chosen, that such types of situation do not occur, where Alice gets back her 1 Bitcoin due to timeout, and also by revealing the key gets the 33 ethers of Bob, which was there in the contract, and in the process Bob gets nothing. So, it is important that the timeout of Bob occurs before the timeout of Alice. And why is it so? Why this asymmetry? It is because Alice is in a powerful position. Alice knows the secret key, but Bob does not know it. So, it is also in this entire exchange, Alice, it is not symmetric. So, there is some asymmetry in the sense that Alice has got more knowledge, and because she has got more knowledge, we have to protect Bob against anything that Alice might do, as a result of which Bob will be inconvenienced. So, that is why one has to set the timeouts in such a manner that Bob's timeout would occur first, and then only timeout of Alice would occur. So, that brings us to the end of this interesting discussion on how we can carry out atomic cross-chain swaps in this lecture. So, if we take a look at a summary of what we discussed, we have explained how hashed time lock contracts work. It is very interesting, and how it can be used for carrying out atomic cross-chain swap operations. And we have taken an example where only two parties are involved in this atomic exchange. In our next lecture, we will talk about more than two parties being involved in the atomic exchange. So, that brings us to the end of today's lecture, but once again I would like to mention that all the web resources, as mentioned from time to time, these are very useful. So, please make good use of those, and you will learn a lot from such resources. Thank you very much for your attention.